Okay, so now we're going to keep continuing these applications, and we're going to look at tension and equilibrium. And the last one we looked at the problem solving. So when you have flexible chords pulling an object, the cord is said to be under tension. So it's basically stretching, and you can see in our little diagram here with the two gentlemen, where one is pulling one way, right? This guy's pulling off here to the right. This guy's pulling to the left. But what happens is internally, right, we have a tension going this way and a tension going that way. So if the cord has negligible mass, the force exerted at one end is transmitted undiminished to each adjacent part. So that's why your tensions would be equal along that entire length. But also understand that cords can't pull, cords will only pull, but they can't push. Okay, and tension will exist throughout a taut cord. Some problems that are seen on these tests will involve equilibrium, meaning, again, forces are all balanced. So that would be like if I was hanging a picture, and I have strings coming off of the picture at angles, right? And they would probably ask me, what's the tension in 1 and what's the tension in 2? All right, but again, just remember the basic problem-solving strategy: draw, sum, solve. Right, so draw the free body diagram, sum the forces in each direction, solve. And then one thing to note is that we have a system. Okay, so a system is any group of one or more objects that are chosen to consider to study. And this is applicable, applied here, because if I'm looking at the bucket on the pulley, like I'm going to look at the bucket, right? That's going to be my system, and I'm going to look at what happens at that point. So if I'm drawing the free body diagram for that point, I'm going to have the tension of the cable up, and then I'm going to have the weight down. And as long as this is in equilibrium, right, my acceleration will be equal to 0. That just means my tension is going to equal my weight, right? And the tension is going to equal the weight of the bucket. So some things on my free body diagram is make sure that if you're going to do anything with the acceleration, that you don't put it on the free body diagram, they put it off to the side. And then in cases with angles, on the scoring free body diagram, you're going to just do your general forces. So it'd be like T2, T1, or however I had it drawn. So I think it was 1 and 2, and then FG. But you may want to notice that T1 and T2 are at angles. You may want to move them over, draw another free body diagram with the components of it. Okay, if you add components onto your scoring free body diagram, they won't award points. Okay, so let's look at an example. So this is what we consider to be a connected object problem. This is very similar to like free Atwood machines. So we have these two boxes connected by a cord. One box is 12 kilograms. The other box is 10 kilograms. And we're pulling with 40 newtons. And we're asked to find what is the acceleration of each box and what is the tension in the cord between them. So we're going to look at the tension here. Okay. So there's various approaches that you can do for this problem. And again, if you go back to the system, right? And so I'm going to say these two boxes are my system. And so my free body diagram that I'm going to draw is going to be my total mass, right? And so what is affecting my total mass? Well, it's going to be that F pull. And the reason why we want to look at it as a system is because acceleration is the same for each inside the system. It's the same. So the acceleration is the same throughout the system. That's what I was trying to say. Throughout the system. So this will allow me to solve part A pretty easily, because when I sum the forces, I only have a pull force is going to equal to be M times A. Now understand that it's the total M, okay, not just the individual M's. So I would say acceleration is FP over MT, and so A will be 40 newtons over my total mass, which is 22 kilograms, and so my acceleration would be 1.82 meters per second squared. And that'll be a positive because I keep forgetting to say this, but make sure you establish positive and negatives by simply just putting a coordinate axes. Now, what we want to do is now we have to find the tension in the cord connecting the boxes, and we want to go easy, right? So we're going to look at whichever one has essentially like the least amount of forces acting on it, and it's going to be box B here, because really the only force I have acting on box B is the tension I'm looking for, okay? But I know that it's accelerating at that 1.82 rate. And so my free body diagram would be tension to the right, and that's it. And I would have normal force up, weight down. But these I'm not worried about because I'm not worried about anything to do with friction. That's later in a couple videos. So it's going to be tension equals M times A, and it's going to be the mass of box B, and tension is going to be 12 times 1.82, and so that's going to be 21.8 newtons. You could do this for the other box, right? Let me change this to a different color. So if I'm going to do it for the other box, the thing is I have 40 newtons here, and then I have this tension here. And so I could also do, it would be 40 minus T equals MA times acceleration. And so my tension would be 40 minus MA, right, the mass of A times acceleration. So it'd be 40 minus 10 times 1.82. And lo and behold, what do you get? 21.8 newtons. You get the same answer regardless of which box you choose. I just chose box B because it has the least amount of forces. It's the quote-unquote easiest one to handle. So again, next set of videos, we're still going to keep working on applications